So now we understand this the attack part, okay, the buffer flow. Now how do we do the countermeasure? So how can we defeat buffer flow? Buffer flow has been there for many years, and there are actually quite many countermeasures and implemented in the system. Okay, so I want you to think about, so how would you put the countermeasure? So now we understand the challenge we face, right? How to actually launch the attack. So we understand the challenge. Now if you can make those challenges even more challenging, and then you may be able to defeat the attack. Okay? So just remember what are the challenges out there? What are the main challenges if you do the attack? What are the main challenges for the attacker? Getting the address. Okay? So here, I need to override this one. Okay? So I need to find the address so I can jump here. I need to know this address. Okay, so we actually do the debugging. We're trying to do that. So now, if you want to make this difficult, what would you do? And we said, so with actually the GDB, we can debug this. Without the GDB, we can still guess this quite easily, right? We rely on one of the fact. What is that fact? Okay, not? Okay, anybody remember? What is a fact that allows us to guess easily?
Static memory allocation.
Static, that's one thing, okay? But I mentioned the one thing. Yes, yeah. This actually make your guess. This is the fixed address. This address fixed, and usually the stack are not very deep, right? As I said, unless you're doing the algorithm homework, right? Otherwise, you won't have a very actually deep stack. So these two together make this address guessing very easy. Now, how do you make this not easy? You cannot change the depth of the stack, okay? That's still depending on your program.
Randomize.
You can change this. Why should I start the stack in the same place? There's no point of that, right? The only point is easier for writing the OS code. I will put a constant in there. Okay, when I allocate the memory, I always use that virtual address. Remember, this is a virtual address. Okay, this address is only meaningful to this process. So what if I just use a different address, right? And so different process. So this process is going to be started with here, with this virtual address space. And another process is going to start with here, another virtual address space. Okay, eventually they're all going to map to the physical address, right? So, but their virtual space doesn't need to be in the same place. Nobody's going to use 0 from 2 4G, right? Nobody's going to use the entire virtual address space. So you will have a lot of holes in your virtual address space that are not mapped to the physical address. So that means any place is going to work. Okay, so this is one of the countermeasure to randomize that. Okay, now with the OS, now they all do this randomization. Okay, so this called ASLR, and there's a term called the address space layout and the randomization. They actually randomize the layout and the address of the stack and the heap. So even if you have a buffer flow, and they make your life more difficult to guess. Okay. So now the address, the problem here is in the past. Okay. Right now I don't know for the 64-bit machine what's the consequence, but for the 32-bit machine, so this countermeasure was developed a long time ago. That time there was a 32-bit machine. So 32-bit machine, if I want to guess, right, and 2 to the 32 is not a very large number. Okay, and also especially if I put another no op inside, I don't need to guess that one address. When I put a no op in here, So any address is going to work inside. So actually the guess is not going to be 2 to the 32. It's much less. So in our VM is 32-bit machine. And in the lab, we ask you to turn that back on. So after you finish this attack, so you don't need to make any change to the attack. Okay? So, and then you go back to your the randomization mode. You turn that back on. You have to run this many times. Try your program many times. Okay? Most of the time it's going to crash because you're going to jump to the some invalid place. Okay? But if you keep running it, and sooner or later, and you're going to hit that point, and you're going to actually still gain the root. Okay? So we ask you to do that, and I actually did that myself. So just I think just 2 days ago, I was a little bit lucky. So I run this. I only capture the end of that. So you can see the cooldown, and once they actually hit the point, once the /bin shell get executed, it's going to stop, right? Because then it's going to wait for your input, right? When you run the same code, the attack code, when it crash, and as long as you run in a loop, it's going to do it again. But once you hit that, and you can see it's going to stop here and waiting for your input. So, and I actually print out the time, the number of tries. So it took me about 15 minutes. Okay, and on my machine here, in a virtual machine, I'm only using 1 core. Okay, and about 12,000 times. Really, is not too much. Yeah, we actually tried this in a workshop, and the results are very, very different. Some people, within 3 minutes, they get it. Some took a few hours, still didn't get it. So you have to bet on your luck, okay? When you do this, if it doesn't work, leave it overnight, okay, and go to sleep, and come back and you'll see whether you have that or not, okay? So sometimes if you after an hour you still don't get it, and cancel it, do it again, okay? Because maybe it's just bad luck. So, and we do have this code. You don't need to write that shell code. We do provide the code for you, and so you just need to put your code in that loop. Okay, we just write a shell script for that. So that's one idea. Okay, so the address space randomization. So what are the another things we can do? What else can we do?
Yeah, the load RT, we said that the compiler adds random values sometimes. To make this random, like between each execution, that will make it more difficult, right?
Yes.
So every time we run the program, it gives different result, different random. Like it takes different size every time, so it makes it more difficult.
Oh, okay. Then you mean the stack itself? Yeah. So that's also, you can also randomize the size of your stack frame. Add a few more things in that. Yeah, that's also a good idea. Yeah. So you can do a lot of these randomization things. Okay. And if you look in the literature of ASLR, there are a lot of things you can randomize. And it doesn't affect the functionality of the program. Okay. So I just want to talk about something else. Okay. So another approach and adopted is called the non-executable stack. This is another approach actually adopted by the OS. Okay. The first one is randomization. This one is based on the fact that you have to put your code on the stack. This is stack. So then you have to jump into here, and the code is here. Stack is used for data, right? Not for the code. Why do we allow people to run code on the stack, right? So yeah, there are maybe some OS they depend on that. In the past, the Linux they do put some of the code in the stack for whatever reason. Yeah, it's not they have to put in there. Maybe it's more convenient, especially if they want to do some exception handler type of thing. They want to push some piece of code into the buffer, into the stack. Maybe that's the reason. And so, but the code doesn't need to be in there. You can put in some other place. So one of the options they do is to turn this the stack into non-executable. And this is supported by the hardware, so you need a hardware support. Okay, so for this block of memory, and you can turn on that bit, hardware bit. That's a non-executable bit, and that's a read bit, a write bit, and then that's an executable bit. So you can say I'm going to turn off the executable bit for this block of memory. Okay, so if you are if CPU try to load the code from here, and it will actually check that bit, and it's all done by the actual hardware, okay, not by instruction, okay. And then if the bit is off, and then the CPU is going to actually basically panic, and then it's going to crash the program, okay. So that's actually called a non-executable stack. Non-executable stack is not a system-wide option, unlike the randomization. When you set that, the entire system is randomized. And this is actually the per application. So when you compile your code, okay, and in the GCC, we actually put on an option. We ask the GCC, after you compile this, please mark the stack as non-executable. Okay, so this marking is actually marked in the application. So when the OS load the application, and it will check that bit, okay, and then you decide whether your stack should be executable or not. Okay, it's only affect your application. Okay, it's not going to affect the others. Okay, because they realize maybe some application they do want the executable stack. So when we do the GCC compile that vulnerable program, we have to turn off the option. Okay, so that option we will make it executable because our code has to run that. Okay.
If the overflow is large enough to write into the next stack frame, then does this not work?
It's going to write into the next stack frame.
Yeah, if the overflow is large enough that it overwrites the whole stack frame for this application and it keeps overwriting further, but it's writing outside of this stack frame, so then.
Okay, so here, no, so here you're talking about stack frame or stack. So here is a stack, and here's a frame. There's a main function, there's a frame, and then there's a full function, there's a frame. So when you overflow, you will have to override the main function, the frame.
Could you end up writing into different applications?
No, this stack only belongs to you. Nobody actually own. You are the sole user of this stack. So once you hit this, so I think you are saying once I hit this one, right? Yeah. Would I go overflow here, right? Yeah. So yeah, in the later of the semester when we talk about the memory isolation, and once you hit this one, your program crash. That's a hardware protection, prevent you from going over the limit of the boundary of the location. Yeah. So once you hit that, yes, you will crash. Yeah, we haven't tried this, but if you put enough data in there, and you will hit that point, and then system crash. Okay. So you don't need to worry. This stack is for you, okay, and it's not going to affect any other memories, any other processes. Okay. So this is called a non-executable stack. Okay. So now for this one, if you cannot put a code in here, but I can still override your return address. Right? Now simply I cannot put my code in the memory anymore. Now can I still defeat this? That means I have to use other people's code, which are already in the system. Okay? If there's a code which is already in the system, I will use that code and to run my damage. Right? What code that is in the memory that you can use? Library, okay? There's a lot of library. That means a lot of code inside. Inside of those library, which particular function that we covered and you would like to use? That's a system function. Very good. So there's a system function somewhere in the memory, and you can easily figure that out, find out the address of that system function. It's a library, okay? And that is already loaded, preloaded. You don't even need to load that. Okay, all the shared library, and they are already loaded. Okay, so you just need to find out where they are, and then instead of jumping to here now you can just jump to this part. And now you can trigger the system to run your function. So, and we know what we want the system to run. So that's being shared, right? We just actually provide a string to the system function, and that system function to run this. That's all we need to do. Okay? So, and that's easy to say, okay, than to do, okay? So the conceptual is very, very simple, but in practice, so complicated, we have to design another lab to do that. Okay, that's why the graduate student, they have to do a second lab on the buffer flow. We ask them to turn that back on. Nice. So you are not allowed to put your code in there. Okay. Now you have to trigger this. Okay. So the difficulty here is not to jump to here. Put in the edges in here. That's easy. Okay. 5 minutes you can do that. Calculate distance is the same. Okay. So that part is the same. What is the challenge here? Yes, passing the input is the most difficult part here. Okay? Now, passing this input, assuming you also know where the bin SH is, it's in somewhere. You can always push this into your stack. It's a data. We can do that. So, and you know where the address is. Assuming you know that. But passing these edges to the system functions turns out to the most complicated one. Okay? And you may think, how is this complicated? Right? Because you can only change these edges when these edges jump to the system function. Okay? So system function is going to look for EBP plus 4 is return address, plus 8. EBP plus 8 is going to be this string. Now you got to put this string, the edges of that string, right on the EBP plus 8. Okay? That means you need to know what the EBP value is when you jump to the system function. You need to know exactly what the EBP value is. Okay? So, and then you can place that. So the complicated is really to understand the EBP pointer. Okay? If we inject our code in here, we don't need to worry too much about the EBP. But in the return-to-libc, now you need to basically know what the EBP is, what the ESP is, and then you can put these edges in the right place. The edges will be somewhere on the stack. Okay, somewhere. Okay, it's got to be somewhere. But that's what it takes to really figure it out. But once you know how to figure it out, and the attack is much easier than actually the one that we are doing right now. So the code you need to write is really much simpler. But the complicated part is the really figure out the edges. Okay? So yeah, I will probably give a lecture to talk about this part, the return-to-libc attack. Okay, this is called the return-to-libc attack. So basically, you do not return to the stack. You actually return to a place inside the libc function. Okay, libc is a standard C library. Okay, and all these common functions are there. Okay, so it's good. So let's look at some of another approach called a compiler approach. We modify the OS. Okay, so now can you modify the compiler to help defeat the attack? Okay, let me just ask you to look at this one. Okay, so I have this code. Obviously, there's a potential buffer flow. What I want you to do is I leave a lot of space in here. Okay, I leave a lot of space here. I want you to modify this code. Okay, the goal is to be able to detect if this buffer is overflown by somebody. I want you to be able to detect that before you return. Because once you hit the return, you're going to jump to the modified return address. Very dangerous. I want you to be able to detect, and then if the buffer overflow happens, stop here. Exit. Don't return. Okay? So I want you to add a piece of code here, add some code in here. You can introduce new variable, global variable, local variable, whatever things. I also want your logic to be generic. I don't want your logic to depend on here. Okay? Although I put things in here, your code written in here should not depending on what I have in there. Because eventually I'm going to turn your solution into a compiler solution. Compiler, if the compiler solution need to depend on the logic, that means the compiler have to understand the code inside. That is very, very difficult. Okay? I want you to come up with a generic solution. So it doesn't matter what I put in here. If there's a buffer inside, buffer is overflown, and I can detect that. Okay, so you can add a new code inside, add a new variable. Right now, I'm asking to do it manually. When we turn that into compiler, we're going to actually modify the compiler, so compiler is going to generate that code automatically for you. Although you write this code, but the compiler is going to add those pieces of code in there and then compile. That's how actually compiler inject its own protection into your code. So you don't need to worry about the detection mechanism, and they will add it for you. Okay? So I want you to give it a try, okay? And then to see whether you can have some ideas, okay? And then we will talk about this. I want to give you 10 minutes to think about this. You can discuss. Let me just clarify this because I see where some students going, and you should not just check this. You should not check the length of this, okay? And so you are not assumed to even see what's inside, okay? To make your code generic, let me cross them out. So you should just pretend you don't know what's inside, okay? So let me put that restriction. So you don't even know there's a buffer. You don't know the size, okay? You don't know there's a variable called buffer, okay? So I want you to do that, and this way your solution will be generic, okay? So continue. So anybody has some clue, some idea? Maybe I have 2 minutes. Maybe you can just briefly mention some idea. It doesn't need to be a complete idea. Any direction you are trying? Anybody? You guys give it a try? Okay.
Well, the problem is that they're setting their address to jump to their malicious code once this ad.
Yes.
So would you be able to save your address at the beginning? And
That's very good direction. That's why I said I like to hear some idea. Okay. So the idea is if we can save that return address, right, somewhere, right, and then before we do return, we compare this, right, that is going to work. The incomplete part is where do we save it? Right? That first part is good, right? So that's the idea is to return address here. We got the return address here. Now, right now I'm inside this function. Before I run this, if I can say, let me save this, I know this one is EBP plus 4, right? I can get that, I can read that value before I run anything inside. Now the question, where do I save it? Where do I save it? Can I save that on the stack? No, okay, that's good. I cannot save it on the stack because stack is eventually going to be override by the attacker. Whatever I put in there, it's not going to work. Where do I save it? Okay, what he meant probably is a heap, right? You mean a heap, right? Save it in a heap, right? So you cannot save in here, but there's a lot of place in the heap space, right? So if you can save that return address in the heap, now before you return, you compare this number with the return address. If it's different, and you should stop, right? So that's very good idea. That's very good idea. So we will talk about this in more detail in the next class. Okay, and so this is one solution. There's another solution, but they all relate to putting something in another place. Okay, and then compare this with that value. Okay, whatever that value is. If they're the same, then this is not modified. If this is not the same, and this is modified. Okay, and both ideas they are similar, but we will talk about that. More important, I still want you to be able to implement that idea in the code. Right now, I'm just saying the conceptually, right? I want you to turn that into the code. So you need to modify that code, put something. When we say the heap, okay, which variable are stored on the heap? Malloc, right? Static value, global value. Those are the things that are stored on the heap. So here, this is actually the function, okay, and this is the memory bar, the string copy, okay. We would like to be able to detect buffer overflow. So we know that's a return address here, which is something we want to protect, and we know the buffer is here. Okay, we know when you overflow this. Okay, the way to actually to overflow this is you cannot selectively override the memory. Okay, when you overflow the buffer, you have to overflow this continuously, right? So you cannot say I'm going to skip this region, and then I'm going to overflow that region, but skipping this region, and you cannot do that. Okay, because the vulnerability is actually it's a memory copy. You have to copy this continuously. Okay, if you know the value here, if you know the value is 50 here, if you know that, and you can override this area using 50. Okay, that's the only way to really not to change the value there. But otherwise, if you don't know the value there, and in order to overflow this part, you will have to overflow that part. Okay, so you are not allowed to selectively actually put your value in there. Okay, so because you rely on the string copy. Okay, so that is a very important fact. Okay, now if we know that's the nature of actually overflow, if I can put something between the buffer and the return address, if I can put something in here, now if you need to overflow the return address, you really have to go through me, right? So based on that observation, now if I can put something between the return address that I want to protect and the buffer, okay? Now, what I need to do is I'm going to actually monitor that area. Before I return, before the return, I'm going to check it. I'm going to check that value, okay, assuming I know the value, okay? And if that value gets modified, that means your buffer has overflowed this part, okay? And very likely you have changed my return address. So if I find that, I will not return. I will just exit, okay? Because when I return, I will jump to that address, okay? So, but exit, and I won't jump to that. So now, what kind of value should I put in here? What kind of value should I put in here?
No.
Put 0 in here? So we just put 0 in here. Would that work? Random number. So it may work for the string copy, okay? But 0 is a predictable. Everybody knows that's 0. Okay, string copy, I cannot put 0 in there, okay? But if it's some other memory copy, like a memory copy, right, we'll not stop at 0. Okay, so it's better to use just random number. If I can put a random number, every time you run this program, this random number is different. Okay, and then before I return, I just check whether that random number is still the original value. If it is the original value, okay, I know you have not actually modified this field. Okay, and therefore you have not modified this field because you have to step over me in order to actually modify this. You cannot skip me. Okay? Yeah, you may be lucky. You may be able to guess what that number is. If you can guess that number and you overflow this area with exactly the same number, yes, I won't be able to detect. But the chance will be low. If this is a 32-bit number, the chance is 1 over 2 to the 32, which is quite low. Okay, if this is not good enough, I'm going to put 64-bit in there. Okay, make it even harder to guess. Okay, as long as I can make it random. So that's actually the idea of the stack guard. So put a guard in here, put a random guard in here. Okay, so now let's actually implement this idea by adding a few things to this program. Okay, we're going to add this guard to every function. Okay, regardless of whether you have a buffer or not, we don't care. I'm going to put that in every function. Okay, this way, if you do have a buffer, you overflow the buffer, and I can detect. If you don't, then I'm just wasting the memory, which is okay. Okay, so let's just change this code. Okay, this is the code. I don't want my code to be depending on the logic of this program. I want it to be generic. I want the same code that I add can be added to every function. regardless of what their functionalities is. Okay, so let's try to do this. First, we have to solve the problem. Before return, I need to compare this area, right? This area is a local variable. Okay, we can easily create an area here. I can let's say we use 32-bit. I'm going to define integer guard. Okay, so that's a local variable. Okay, if you write this program like this, okay, this guard is not guaranteed to be right below the old EBP, right? And the compiler can actually change it. So this is the old EBP is pointing to here. Okay, and this is actually the beginning of your local variable. Okay, to here. The compiler may actually move this to some other places. But since eventually we're going to implement this inside the compiler. Okay, we will make sure. And this number is allocated right below the EBP. Okay, so we're going to do that. And now before we return, we're going to check if guard equal to something. Okay, and of course we need to actually initialize guard equal to something, right? So let's say equal to x. I'm just going to use this x here, and I'm going to check if this is the equal, and I'm going to return, okay? And else, okay, I'm just going to do the arrow curve. The question is, where do I store x? I just put x as abstract things in here. Where do I store x? X contains a random number, right? Remember, we want this to be a random number. Okay, now x, this random number has to be stored somewhere.
The BSS segment.
BS, okay, very good. So we need to store that in a different place, not on the stack. You should never store this x on the stack anywhere. Okay, what if I stored x here? Would that work?
No.
It's not going to work because when I overflow this, I will overflow this area as well. Okay, as long as I make this value and this value the same, I can defeat your protection. Okay, so I cannot put this x anywhere on the stack. So when you say the BSS, so what kind of variable are stored in there?
Static variables.
Static variable, global variable, right? So all we need to do is define, let's say we use a global variable. Okay, we're going to define something outside of this function. A global variable, we're going to define something called in secret. And we're going to initialize the secret inside our main function. Okay, and so initialize with a random number. So basically, when your program starts, okay, and it will initialize this global variable with a random number. Okay, and you can generate a random number. Okay, and after that, that random number is stored in a heap because this one is going to, the variable is going to be stored on the heap in a different place. Now every time when you enter the function, and you're going to set this value, okay, this guard equal to the secret, which is a global variable. And here you can do the same thing if this still equal to secret. Okay, and then that means that is not modified. The guard is not modified. If the guard is not equal to secret, that means it's modified. Okay, now we should not actually return. Okay, so the trick here is you got to store something beyond the stack. Okay, store something which is not predictable. That's why it's got to be a random number. Okay, you cannot put a constant in there. Okay, so a common mistake is some people put a constant. Okay, and put 0 or some other constant number. Okay, you should never hide a secret in your code because your code can be readable. Okay, people can read your code. Okay, so but if you can dynamically generate a number, that's okay. Okay, so is this clear? And that's how basically how you write the code. Okay, if I modify this manually, But if you look at the code, is this code depending on the logic here? Does it depending on that? It doesn't, right? It doesn't matter what you have in here. I'm going to have the same thing, integer guard and the guard equal to secret. And for every return, I'm going to actually turn that instruction into if guard still equal to secret. So my code, the code I added, has nothing to do with your logic. If you can have that property, and you can integrate this into your compiler, you don't need to actually ask the developer to type all the things manually in their code. You can let the compiler add those code and on top of the existing code. For every function that you implement, compiler can add a few things here, add a few things here automatically. Okay? And they don't even need to add this at the C level. They directly add it at the binary level. Okay? So this way, this protection is built into your binary. Okay? So let me just show you exactly what the compiler does. And this is actually what the compiler does. And this is actually the full function. Okay? And I compile. Okay? And you can actually easily compile this using -s option to compile a C code into assembly code. Okay? And then you can actually print out the assembly code. And here, and I want you to look at here. Okay, these are the actually in the bold font. Okay. This one is going to move this GS at offset 20, and this GS is a segment register. Okay, and this actually contains the base point for the heap. So basically, it's move some value from the heap to the EAX. Okay, and then it move this EAX to the EBP -12. Okay, so EBP is here. So RA is here, return address here, EBP is here, and it's actually -12. It store the value, the guard in here. And I don't know why they leave some space in there. It's an integer, 32-bit. Okay, but they store this integer into EBP -12. Okay, so, and then this XOR EAX just clean out the EAX to make sure the secret is you won't be able to get a secret from the register anymore. But this is really is the guard equal to secret, equivalent to that. Right? And this is the region for the guard. And the secret is already initialized and put in that location, which is in a different segment, not on the stack. Okay? So now after this, okay, this is actually is the code of that full function. Before the return, now if you can see, it move that value, and they call it canary. Okay? So in the stack guard, it's called a canary. And so it moved that value, okay, -12 to EAX again. Basically, move this into EAX register. Compare XOR, basically check whether these values are the same. Because if you XOR and EAX with this secret, if the value is 0, that means they are equal. Okay? Basically, if you XOR something with itself, it should be 0. If it's not 0, that means these two numbers are not the same. So it XOR and check whether they are equal or not. If they are equal, that means the guard is still the same as what is stored in that GS at offset 20. And then it will just jump to L2. L2 is actually the return instruction. Otherwise, it will call this one. It's going to call the stack check fail. Okay, and it's going to report error. It's going to exit. Okay, so it will not return. So that's actually the error, the handling part. And that's what actually compiler added. Okay, this part and this part, they are added by the compiler to your code. Okay, so if you do not disable the stack protection, right? When you compile the code in our lab, you have to disable that, right? And if you do not disable, this is what is going to be added to your code. So your code has the protection by itself. And this is a very good idea. Okay? So many other the idea that we talked about, and randomization, they have a limitation. the non-executable stack, they have limitation. Okay, but this one is quite good. Okay, and it's actually integrated into a lot of compilers, Windows and Android, and they all actually have that built in. Okay, so I just want to show you this. There's some nice idea out there. Okay. Yes.
Can I ask a question about the previous slide?
Yes. This one, yes.
So if I know the secret and I put like in the bad file, I put in the red area the secret number, I will defeat this method. Right?
How do you know the secret?
Like if I'm doing GDB and I stop the program after defining the global variable, but before copying the buffer, so I can stop the program here and go to the bad file.
Yep.
At that time, I know the secret. And
Yep.
like, load the
If you GDB a program, you can find the secret number.
I can.
Right? You can find the secret number. But would that actually defeat this protection or not? I'm going to leave to you guys to answer. No? Okay, why? Okay.
It's random every time.
It changes every time. When you GDB that program, that random number is 0x559. Now if you run it again, it becomes 69. The value is always just different.
But I don't want to run it again. I will use the same
Okay,
time.
then somebody else can answer that. We cover that. So he's saying, I'm using GDB to debug that program, and I find the number. Now I can defeat this, actually, the protection, right? And that is right. Okay?
You mean I cannot debug the SetUID program?
Yes, that's to answer your basically your own question. This is the kind of question that I would like to ask in the final exam or in any exam, okay? So because this shows you whether you really understand that or not, okay? And to defeat that, there's a lot of actually the countermeasure in the system. If the OS does not disable that, and it's going to be a disaster. Anybody can debug a SetUID program. That's going to be a problem. And that's why the debugger mechanism, okay, need to have the OS support. And that OS support really put a countermeasure there. If you are a normal user trying to debug a privileged program, you are not allowed to do that. Okay? Because debugging mechanism is going to allow you to actually put some of the tracing that program. Okay? And that requires OS support. Okay? Normally, you can't just actually debug another program. Okay? It requires at the OS, the built-in mechanism inside the OS to allow you to even to be able to debug another program. Okay? So that's why when you debug a privileged program, debug is going to run, but it's going to drop the privilege. Okay? So you can still debug that program, but it's not going to actually run with the SetUID, the root privilege. Okay? So otherwise, none of this protection matters. Because if you can go there, you can even change the program. You can change the variable, right? It doesn't matter now. Okay, so very good. Okay, so that's a very good question. I'm glad you guys can answer that. Okay.
But to exploit a buffer overflow, it doesn't have to be a SetUID or a privileged program, does it?
Has to be let's say if I'm attacking a program which is running with my privilege, what is the benefit? Right? No benefit. I can just modify this directly, right? So if I'm attacking a program which is running with my own privilege, really there's no gain. Yes, I can debug, I can change the value, I can find the secret value, but there's no benefit. But if I can debug your program, and that's going to be a benefit, because that program is running with your privilege. Now, if I can debug that process, now I can change the behavior of that program, and therefore I can let it do something which I want to do, right? So it doesn't need to be the root, but if the process is running with a privilege that's not mine, and if I can attack that program, I gain the privilege. Okay, so you should consider privilege as a more general term. So the privilege is something that I don't have. Okay, whether it's another user, whether it's a root user, whether it's just a nobody. That's a user called a nobody. Okay, so it doesn't matter what that user is, as long as that is not mine, and I gain a privilege, because normally I cannot do that. Okay, so you should consider the privilege in that term. Remember, in the reverse shell attack, right? We are attacking the web server, right, from remotely. That web server is not even running with root privilege, but it's running with a privilege that the remote user doesn't have. So to the remote user, that is a privilege. Okay, so you should consider this privilege in that sense. Okay, okay, very good question. So now if you understand that, I'm going to ask you to answer this question. Okay, so this is not a quiz. Quiz is not here yet. Okay, so, but I want you to look at, this was actually the last year's final exam, the question 1. Okay, final exam 5 point. So here's an example of what final exam question you're going to see. And this does come out from the student's mistake. Okay. So first I want you, after you think about it for a minute or two, I want you to tell me is this safe or not. Okay, basically, the students who wrote this is trying to implement the stack guard. Okay, so there's a guard here. Okay, there's a guard here, just like what I did. Okay, so the student understand the secret should not be put in a stack. So he using the malloc. Okay, so the secret is actually is in the memory. So this is a stack, and this is a heap. Okay, so malloc is going to allocate a memory on here on the heap. Okay, and that is point to here. And now assign the secret value inside of this. The secret is actually put in here. The random number is actually put in here, not on the stack. So the student was doing the things right. Put the secret in another place. Okay. Now, and it will initialize the guard with a secret value. So now guard is going to equal to that random number now. And then after that, it's going to check whether guard is still equal to the secret number. Right? It does exactly what we did, but in a different way. I was using a global variable. The student was using a pointer which points to something on the stack, on the heap. Right? Now I want you to think about, is this safe? Can you defeat this? If this is how it is implemented, can you defeat this? Without knowing that random number, of course. So think about this as the guard is going to be here, the guard, okay, and the secret is going to be here. The secret variable is going to be here. Of course, this value is going to be point to here, okay, and then the buffer is going to be here, okay. So
couldn't you kind of like use GDB to find the location? Like
okay, you can find the location.
And then
okay.
what you do is you just, because it's used, the pointer is stored on the stack, so you just copy it and then you could always point to the heap, and that's how you would defeat it.
How do you cannot change this code? You cannot change this code. So now, how do you overflow the buffer? Show me. How do you the guard is going to be an integer. The guard is not going to be a pointer. Okay. So show me how you can overflow this, so you can actually defeat this check. Basically, your goal is you want to make this check to still be true. Okay, you want this guard still equal to that. Okay, equal to the star secret. Okay, you want that. Secret contains an address. Okay, the star secret means and find the value which is pointed by this address. Okay, the value pointed by that address. Okay, that's going to be an address inside. Address. And the guard is not a pointer, so guard is inside the guard is a value. Okay, inside the secret is address. Okay.
You can change the address of the secret.
Mm-hmm.
Make the secret point to somewhere in the stack, and then make the guard and that process in stack will equal.
Very good, very good. So think about this. The secret contains an address is also on the stack, right? Now, I cannot let this point to this one because I cannot guess this. But if I can overflow this field, I can actually let this pointer to the guard, right? I can find these edges. Okay, as I said, we can find the edges. When I overflow this secret field, I will just, if this is 0x90, if this edge is 0x90, I'm going to 90 is a no op. Okay, 98. Okay, so I'm going to put a 0x98 inside, right? And now this secret now is going to point to this guard. Now you're going to check this. If guard equal to guard, basically, and so I don't care what is inside the guard, but guard is going to equal to guard. Okay, this is the guard, and this edges now point to the guard. Okay, so in this way you can just completely defeat this mechanism. Okay, so you can see the heap is the secret number is stored on the heap, but somehow you store the pointer on the stack, and I can change that pointer. Okay, so that's why the solution is much better, safe, because that global variable is not on the stack. Okay, it's completely on the heap.